start. All right. Happy Monday. No Monday next Monday, so that's nice. And just because I would hate for someone to show up on Friday when we're not going to be here, right? We're going to be out doing something way more fun, whatever that is to you. I'll post a video. Kind of depends on how far we get today, so it'll just be a continuation of today and going back into the textbook chapter 5. And so we'll do systems of linear equations today, but we'll wrap up linear equations. There's that last page that we didn't finish, and so we'll start there. Because, in case you don't believe me, here's where we ended on Friday. And I said, try this page on your own for Monday. And here we are on Monday. And I was like, oh, dang it. Or totally did that. So let's jump in there. This will be a way of reviewing some core concepts from Friday as well. So linear equations continued. And then I'm so worried that you'll show up. Usually students are really good about not coming to class when you guys are good about keeping track of that. But
Sorry, there's no class on Friday.
No class on Friday. I'll post a video on matrix algebra for you to watch, but we're not meeting because it's the Friday before a long weekend and no one wants to do that. So you can watch it at your leisure. And then we'll review it when we get back. Okay. Whoo. What were we doing? We have an absolute value function, right? 3 times the absolute value of x minus 1, and then plus 1 is greater than 7. So here we're doing a mashup of an inequality with the absolute value function. To solve an absolute value function in general, right, we can find where does this thing equal 7, okay? And then if we kind of think back to what a general absolute value function looks like, this one, not to show off or anything, well, kind of, I guess, is going to be moved over to the right by 1 and up 1, and then it's got a V shape, and the slope of 3 makes it steeper, but something like this. It is helpful to know what this thing's going to look like, just so you can kind of check your work, but you don't have to. And we want to know, where is it greater than or equal to 7? This thing is greater than or equal to 7 in 2 sections. Yeah. Now, how I like to solve these is I find these points, right? I find where it's equal to 7, and then I use test points. So I don't need to know what it looks like. It's helpful, obviously. But if we kind of pretend that we don't know what this thing looks like, then we can just use test points. Okay. So to solve these, to solve absolute value inequalities, one, find the equality, or solve for the equality, which in this case is 3 times the absolute value of x minus 1 plus 1 equals 7, is what I mean by that. That's going to give me these values of x. Right? Those values that make it 7. And that's where it's going to switch, right? Even if we pretend we don't know what it looks like, right? We understand that those would be where it switches from being greater than 7 or less than 7 at 7. And then use test points. To find the intervals where the inequality is satisfied. Because I didn't give myself very much room, I'm gonna do step 1 on one side and then beside it step 2. And so I've got 3 times the absolute value of x minus 1 plus 1. I'm gonna force it to equal 7. Now I will say, you don't have to follow these steps. If you're comfortable with working with inequalities and moving things around inequalities and then working with absolute value inequalities, that's fine. You're going to get the same answer, but I find that that's typically kind of difficult. So this is how I do it. To solve, maybe I should add a note. To solve absolute value inequalities, I follow these steps. Like many things, I'm open to if you have a different method, as long as we arrive at the same answer, that's fine by me. So what do I have to do to solve this equality? First thing I need to do is I need to get the absolute value function on its own. And so I'm going to subtract 1 from both sides and then divide both sides by 3. And so I get 3 times the absolute value of x minus 1 is 6. And then, so the absolute value of x minus 1 is 2. Once I'm down to the absolute value, I know that the positive version of x minus 1 has to equal 2, but also the negative version of x minus 1 has to equal 2. And if you like to make the 2 negative, that's fine. It's just not how I was raised, academically raised, I guess. And so the positive version, x minus 1 is equal to 2. That's easy enough. X is going to be 3. But then the negative version, negative x minus 1 has to equal 2 as well. But you can see, even if you preferred to make the 2 negative, that's the same thing. You've got an equal sign here, so you're allowed to move things around and you don't have to switch anything. But for consistency, I am going to use the same method that I was last day, which was mere days ago. Feels weird. Negative x plus 1 must be 2. And so negative x must be 1. So x must be negative 1. What does that tell me? Tells me that here, this isn't correct then, but the idea stays the same. Those points where it equals 7 must be at negative 1 and 3. But even if we pretend we don't have this, right? See how I drew it? I drew it bad because I didn't care about the slope. So obviously the negative 1 should be on the negative side. That's okay. It's just to get an idea of this thing. Okay. So step 2, what you're going to do, and we did this For other inequalities with the test points, right? We took test points in a plane and we plugged them in to see if they satisfied the inequality or not, right? And so we're going to do the exact same thing. And so on a number line, you're going to plop down your x's that you found. So -1 and 3, giving yourself enough room in each of the sections to do math. Okay. In particular, you need to be able to do 3 times the absolute value of x plus 1 equals something in each section. Right? So test points. So use test points to find the intervals where the inequality is satisfied. Anything less than -1 is going to work. I encourage you to pick kind of easy values of x. For example, what if I did, I don't know, -2? These points, you can pick whichever ones you want. You just want to pick a point that represents that whole interval, right? And so obviously my go-to between -1 and 3 is 0, because I love 0. And then 3, let's spice things up and go with 5. I don't know, whatever. Okay. The test points can be any values. So if you don't like those points, that's totally fine. You can pick different values. So now what you want to do is you want to check this inequality. So we've got 3 times the absolute value of x minus 1 plus 1. And I'll write it out for this one, but usually I get lazy and I just write out with the x at the test point immediately. That's lazy of me. But otherwise I'd have to write it out 3 times, and that's technically correct. But this is going to be 3 times -2 minus 1 absolute value plus 1, which is -2 minus 1, working with the absolute value inside, is -3. But the absolute value of -3 is 3. So this becomes 3 times 3 plus 1, putting me at 10, which is greater than 7. Which tells me that this whole interval satisfies that inequality up to -1, but not including -1, because at -1 it was equal to 0 or 7, sorry. All right. And so here, this interval, not including -1, satisfies it. I have a hunch then that the next interval is not going to work, but we're going to do the math anyways. Fine, I'll be proper. 3 times the absolute value of x, oh, nice try, Emily, -1 plus 1 is 3 times the absolute value of 0 minus 1 plus 1. Absolute value of -1 is 1, so we get 3 times 1 plus 1. 3 times 1 is 3 plus 1 is 4, which is less than 7, so it's bad. Which we already suspected, knowing kind of the anatomy of the absolute value function. But notice how you don't need to know what it looks like for the test points to work. So then, for this last section, which we suspect will work again, right? But let's confirm 3 times the absolute value of x minus 1 plus 1 is 3 times the absolute value of 5 minus 1 plus 1, which is 3 times 5 minus 1 is 4 plus 1. And 13 is greater than 7. So that's true, which tells me that this interval is also appropriate, but not including 3, because that's where it's equal to 7. And from this inequality, we wanted it strictly greater than 7. So then the interval then is going to be from negative infinity up to -1, not including -1, and then from 3, not including 3, up to positive infinity. So negative infinity, oops, bad infinity, up to -1, not including -1, so round bracket, picking up at 3 again, going to infinity. Okay. Did you already try these at home, or do you want a moment to try the next one on your own? Crickets. How about just a moment to get started on the next one on your own? Just for a little warm up. I'll pause the recording though, because yikes. All right. So we want to know, how about I do it without drawing it to show you that it still works? Although, like I said, it's helpful. We want to know where the absolute value of x minus 3 minus 5 is greater than 0. You can solve this with just the inequality, but like I said, I think it's more difficult, but if you prefer it, that's totally fine. And so here I'll say can or could solve with the inequality, I guess, period, but I'm not going to. Step 1 for me is isolating the absolute value of x minus 3 minus 5 is equal to 0. I find where it's going to switch from being greater than 0 to less than 0 or vice versa. And so I get the absolute value of x minus 3 is equal to 5. I need to consider both the positive and the negative version of x minus 3. So x minus 3 is equal to 5 means that x must be 8. And negative x minus 3 must also be equal to 5. Negative x plus 3 must be 5. So negative x must be 2. So x must be negative 2. Step 2. I plop down -2 and 8. Pick convenient test points. Let's go for -4, 0. And I like them to not be equidistant. Let's do well, now I'm drawing a blank. Let's do 9.
Is there a reason that you just choose random numbers, not just one less than one over?
I just want to show that it can be different from 1 less than 1 over. But usually I do go one less one over, and that's easy.
There's any options that could not work?
Nope.
It
I mean,
doesn't always work.
You could do like negative 4.897 if you wanted. But why?
So
But you want to pick convenient values of x. So what I mean by convenient is if you had, for example, if you had x plus 3, then of course a convenient value of x would be 3, or sorry, minus 3. Minus 3 plus 3 makes 0, so then I don't have to deal with it.
technically, you don't really have to do step 2. It just the answer is -2 and are infinite.
Well, but that's if you know enough about your absolute value functions, but you could have something like this, right? Or in this case, what if you wanted to know where it's less than 0, then even if it's facing up, the behavior depends on the function, right? So without having to draw them, because no one likes drawing the graphs, right? Then the test points are safer. You don't have to, you can do test points in your head, but you would still be using test points, so why not just write them down, right? You don't have to do step 2, but I think it's the easiest kind of most mindless way of doing it, at least for me. So what do you get? You get the absolute value of x minus 3 minus 5. Oops. And I'm going to do the equal sign down here because I don't have a lot of room. The absolute value of negative 4 minus 3 minus 5 is negative 7, but that is the absolute value of negative 7 is 7. So 7 minus 5 is 2, which is greater than 0. Same thing for the next region, x minus 3 minus 5, or absolute value, sorry. Absolute value of 0 minus 3 minus 5. Negative 3 is 3 minus 5 is negative 2, which is not greater than 0. I'll use that. And then same thing here. Absolute value of x minus 3 minus 5. 9 minus 3 minus 5. 6 minus 5 is 1, which is greater than 0. So then the interval is going to be negative infinity, and we wanted to exclude 2. Helps to draw 2. Or sorry, negative 2. I snuck that in. Sneaky. Union 8 to infinity. Oops.
Let's show that process how we got the answer of the exam.
Nah, it's okay. Because what could you do? Like I said, you could solve it with the inequality, which would look like this. I'll add a page. Oh, I need lines. I'm not going to get them, am I? Solve with inequalities. So you could I've said, okay, the absolute value of x minus 3 minus 5 has to be greater than 0. As long as I'm not multiplying or dividing by a negative, I don't have to flip the inequality, right? So far so good. I've got the absolute value of x minus 3 is greater than 5, which means that x minus 3 has to be greater than 5, which means x has to be greater than 8. I'm adding 3, so that's safe. And negative x minus 3 has to be greater than 5. This is where it gets a little bit trickier. Negative x plus 3 has to be greater than 5. Or if you prefer, you could have moved this negative over right away and change the inequality, right? I'll do it the old-fashioned way. Negative x has to be greater than 5 minus 3, which is 2. So then x has to be less than negative 2 when I multiply or divide by that negative to bring it over to the other side. So x has to be greater than 8 or I guess x has to be less than negative 2. So you get the same thing, negative infinity up to negative 2, not including 2, union 8 to infinity. Yep. That's fine. I just think, or I know from experience, people don't like working with inequalities because they're hard. Right? But if you prefer, you can try the first one too, right? Isolate the absolute value in the inequality and make sure that you get the same intervals. That's fine. But I follow these steps. Nice. Okay. How about just gonna snag this. And bring it onto this page. And I'll just say, move to next page. Just because otherwise there's kind of a jump between the previous example, the new one, and then. Ugh. So what we talked about last week was if I want to find the intersection of two lines, right, y equals mx plus b and y equals nx plus c, maybe, right, then what's my kind of go-to move is I like to substitute one into the other, solve for one of the variables, and then plug that back in. Okay. And so now we can use that same method for more than two unknowns. Okay. So when we solved for the intersection of two lines, we had two equations and two unknowns, right? We had two lines and then we had x and y that we had to solve for. And so we can continue to use substitution, or if you have learned about elimination, that procedure instead, that's totally fine. I think that it's harder, but it's what we're going to start doing in the next section. So I wanted you to see both to solve for n unknowns, as long as we have at least n unique equations. Okay? So 3 equations, 3 unknowns, 4 equations, 4 unknowns is kind of the typical setup. You need to have as many equations as you have unknowns or more. So to find 3 unknowns, we need 3 equations. three unique equations. Okay. So got this word problem. Uh-oh. I think it's kind of cute. I stole it from a textbook, obviously. The Upside Down Company, because they work with down, specializes in making down jackets, ski vests, and comforters. The requirements for down and labor and the profits earned are given in the following chart. So for each jacket, it requires 3 pounds of down, 2 hours of labor, but you get $6 in profit. Hopefully more than just 6, but 6 units of profit. Maybe it is just 6, I don't know, doesn't matter. So what we're gonna have, and so we know the requirements for the vests and the comforters. Okay? And so each week, the company has available 600 pounds of down, 275 labor hours, and we've got this goal of a weekly profit of 1150 or 1,150. How many of each item should the company make each week? Are we going to set this up? So now I have 3 unknowns. Right. First thing that I'm going to kind of lead you down the path of is let's let jackets be X and vests be Y and comforters be Z. X, Y, Z. We were also told that we have a total of 600 pounds of down. I could spend it all on making vests if I wanted to, right? Or I could spend it all on comforters, but overall, I only have 600 pounds of down. I only have 275 hours of labor, and I've got a goal profit of 1,150. This is looking more and more like y equals mx plus b, but I've got more than one variable, right? And so what we're gonna do is, let's see how I set it up all fancy. Uh-oh. Mix up my pages. Good. I have a total of 600 pounds, and I use 3 times X, 2 times Y, and 4 times Z. And that total, that sum, has to be 600. I want to use up all my down, right? And all my labor hours. And so what we're going to do is we're going to set this up as we're going to be given 3x plus 2y plus 4 times z is equal to 600. This is the down linear equation. We're used to seeing linear equations where it's just a straight line, but now our linear equations are referring to just powers of 1 on my variables. And so that's what we're going to call a linear equation. But now I have 3 unknowns, right? Which means I'm going to need at least 3 equations to be able to solve for 3 unknowns. Yeah. So what if I did the same thing with the time that they take? Then I have 2x plus, did I write? I didn't write the coefficient of 1. You can in the beginning if you want 1 times y, but I'm just going to skip to y plus z is 275. And this is the time equation. And they contribute different amounts to the profit. my gut reaction is that you actually should make a lot of vests because you get as much profit, but they take one less hour and one less pound than the one making the same amount of profit. Just kind of gut reaction, right? But let's see here. Let's see. So the profit equation is going to be 6x plus 6y plus 2z is 11. I'm forcing it to be 1150 for the profit equation. Okay. There are many different ways to solve this. So I do want you to try it just for a little bit. You can use elimination if you're familiar with it, but I like to use substitution. And so how that's going to go in general is I like to solve for one of the X's, Y's, or Z's. And usually I kind of pick something convenient. I'm drawn towards either Y or Z in this second equation. Now it is helpful if you label these equations 1, 2, 3, for example. So if you solve for, let's say, Z in the second equation, then what could you do? Then you have Z equals 275 minus 2x minus y. All of a sudden, you just have something in terms of x and y. So then what if you substitute those into here and here? Not back into itself, because then you're just going to end up where you started, right? But you can substitute that value of z into the first equation and the third equation, and then you simplify, and then those equations will just be in terms of x and y. And then you do the same thing again, solve for one of those two, plug it into the other one, and then you'll find what one of the variables have to be, and then you can kind of chain link it back up to solve for the other variables. So I'll give you just a moment to give it a whack, and a moment being, I don't know, 5 minutes. 4 minutes, because it's 46. I'm always worried I'll forget to start recording again. Okay. I will make a note that there are many ways to solve this. That doesn't look like many. So here's one. I like to kind of say what I'm gonna do, right? And kind of outline it that way. And so I'm going to use the method that I mentioned earlier. I'm going to solve for z in equation 2. So I have 2x plus y plus z is 275. So z is 275 minus 2x minus y. I'm going to need another page. Now I'm going to substitute that, right? So I grabbed this z and I'm going to substitute it into here and here. So equation 1 and 3. So I'm going to substitute z into 1 first, and 1, I'm just going to cheat and copy it. But it was not what I copied. Paste. Oh, I see. I have to write it out. 3x plus 2y plus 4z is 600. But I'm gonna use this z instead. And so I get 3x plus 2y plus 4, and I'll use a different color, times 275 minus 2x minus y is equal to 600. I'm going to simplify this. And I've already done it once, so I'm just going to try to copy it out properly. 3x plus 2y plus 1100 minus 8x minus 4y is equal to 600. Now here's where I like to kind of consolidate and make it set equal to 0. That's an unnecessary step, but I don't know. I just, that's what I do. I don't know. But like I said, there's many different ways that you can do it. So 3x minus 8x puts me at negative 5x. 2y minus 4y puts me at minus 2y. 1100 minus 600 is plus 500 equals 0. If you wanted to, you could have negative 500 on this side. It really doesn't matter. Now I'm going to do the same thing, but I'm going to substitute z into equation 3. Substitute z into 3. Now what was 3? Let's see if it'll let me. Hey, copy that. My iPad's misbehaving, but not as bad as it was earlier this week, so, or earlier last week. So I guess I can't complain. 6x plus 6y plus 2 times z, which is 275 minus 2x minus y. Is 1150. If you expand and simplify, I get 6x plus 6y plus 550 minus 4x minus 2y is 1150. 6x minus 4x is 2x. 6y minus 2y is plus 4y. 550 minus 1150 is minus 600 is equal to 0.
I divided by 2
Divide by 2?
on the last.
Oh no, I'm collecting like terms, so I'm doing 6x plus 4x.
Oh no, I meant like after that.
6y minus 2y. And then 550 minus 1150 to bring it over to the other side.
Yeah, I meant like from 2x plus 4y minus 600 equals 0. I put 2 on every side. So I put 2x plus 4y equals plus 600. Then divide by 2 on every side. So it'll be x
Oh,
plus
here.
ready.
Yeah.
Then divide by 2 on every.
That's fine. You don't have to, although you will eventually if you decide to solve for x or y using one of these. But yeah, so you will eventually. But like I said, there's many different kind of, whatever comes to you naturally is what you should do. This one is nice, right? Because you can solve for x relatively easily. right? And so, sure, let's do that. What did I do? I did do that. So, I'm gonna solve for x in the new 3. Right, this is still equation 3. It's just been manipulated. Right. And so I get 2x plus 4y minus 600 is 0. Solving for x though, I get 2x is 600 minus 4y. So x must be 600 minus 4y divided by 2. But I have to divide both sides by 2, or both things in the fraction. So 600 divided by 2 is 300 minus 4 divided by 2 is 2y. Now I have x in terms of y, which I want to put into one of the functions that only have x's and y's, because then I'll whittle it down to just one variable, right? And so looking here, this is kind of my new one, right? We didn't do anything to the second equation, and so I'm going to leave that one alone for a little bit. But I will take this little guy, copy, and now I'm going to substitute x into the new first equation, which was this. Now, if x is 300 minus 2y, I'll use a different color to show it. X can be replaced with 300 minus 2y. Minus 2y plus 500 equals 0. It's such a good feeling when you're down to just y's, because now we can expand and simplify, right? And so I get negative 1500 plus 10y minus 2y plus 500 equals 0. 10y minus 2y is 8y. Doing kind of some maneuvers. 1500 minus 500, or negative 1500 plus 500, but moving it over to the right-hand side. Either way, you're left with 1000 on the right-hand side. So then y must be 125. Which means you're going to make 125 vests, right? And if you're going to make 125 vests or y's, then you also know how many x's you're going to need, right? And so here, x was 300 minus 2y. So x must be 300 minus 2 times 125. I get 50. So we know x is 50 and y is 25. And we also know from way at the beginning, z is 275 minus 2x minus y. Now I have a value for x and I have a value for y. And so I can easily solve for z, 275 minus 2x minus y. $275 minus 2 times 50 minus 125. I get a z of 50. 50 jackets, 125 vests, and 50 comforters will get you the desired profit of 1150. I encourage you to check your work, right? Because these X, Y, Z combinations have to satisfy all of these at the same time. Right? So it's the intersection. Okay. So we can check. Although I kind of didn't want to use a, why not? 3 times 50 plus 2 times 125 plus 4 times 50 is 600. Two times 50 plus 125 plus 50 is 275. Has to be true for all of these. 6 times 50 plus 6 times 125 plus 2 times 50 is 1150. Nice.
It doesn't matter which one you grab, just grab the one. That is.
Yeah, you can solve for any one of these as long as you plug it into the other two equations, right? You don't want to plug it back into itself because you're just gonna kind of loop onto yourself. But the reason I was choosing between Y and Z. I mean, in theory, you could have solved for X in the first equation, but what would you have? You'd have 600 minus 2Y minus 4Z divided by 3. There's no cancellation there. So then you're having to lug that fraction around in all your substitutions, and what a mess. Yikes. But it would work. You would get there in the end. But I like to pick kind of clean values. Well, like you said, you could have solved for Z in 3, right? That would probably 1150. Yeah, should divide by 2, right? To something nice to work with. And then these guys would reduce. But because we had these Y's and Z's just with coefficients of 1, usually those are the ones I gravitate towards. But yes. A lot of me trying to get into your brain. See, okay, what were you doing here? All right. Try to follow along. So you're going to be really nice to me, right? And you're going to tell me what you're about to do, right? As long as you follow through. Okay. Any questions about those before we kind of keep doing the same thing, but in a more sophisticated way? Okay. So, we're going to build a little bit off of that example. So this is the set of notes from today. If you don't have them, they're up here. So we solved the system using the substitution method because it's what I like to begin with. And I know you're thinking, wow, only 3 pages long? How luxurious. Yes and no. We're gonna do a lot of writing on the side, which is why I had to grab those papers. Okay. So today we're going to talk about what's called Gauss-Jordan elimination method. And so we solved the previous system of equations. So when I have just 3 equations like that, and they're all related to the same system, we call it a system of equations. And so we solved it using the substitution method. And so another method that we're going to start to gravitate towards is called the Gauss-Jordan elimination method, which we're going to be repeatedly simplifying the system using, and I copied this because I thought it was so cute, using so-called elementary row operations until the solution stares us in the face. Cute. So we're going to solve systems of linear equations by just repeatedly following the same or applying the same row operations. So there's only 3 to keep track of. There's only 3 things you're allowed to do. And they're all pretty intuitive. And so as long as you're not changing the solutions, you're allowed to do it. Okay? And so they're called elementary row operations because they're all kind of using basic elementary algebra. And so first thing you're allowed to do is you're allowed to interchange any 2 equations or rows, if you like to think of them that way. So you're allowed to move things around, right? Move the equations around each other, that's fine. Then you're allowed to multiply an equation or a row by a non-zero number, right? Kind of sneaky tricks like, oh, okay, I could divide that whole equation by 2 to make it a little bit easier for myself later on, right? We're allowed to do that. Okay. If you want to eliminate fractions, you can multiply by the denominator, right? Do kind of sneaky things like that. And you can change an equation or a row by adding it to a multiple of another row or equation. Now, the idea is to transform a system of linear equations into diagonal form by repeatedly applying these elementary row operations. Now, what's diagonal form, you might ask? Diagonal form is something like this. Okay. And so diagonal form has your x, 1 times x, right? Technically a coefficient of 1 times x plus 0y plus 0z is 50. 0 times x plus 1 times y plus 0 times z is 125. And 0 times x plus 0y plus 1z is 50. So we could have written our equation or our solution to the system like this, right? We found that x had to be 50, y had to be 125, and z had to be 50, right? And so we can write our solution like this. And so as long as we're stacking our x's on top of our x's and our y's on top of the y's and our z's on top of the z's, I wrote too big here, but then we'll be able to add and subtract the rows from each other to eliminate the other terms, right? Because our goal is going to have x, y, z on the diagonal like this. To show your work, you're going to use abbreviations for each row, like R1 for row 1, R2 for row 3, for row 2, et cetera. Okay. Just like we did earlier, right? We gave each equation 1, equation 2, equation 3, so they were easier to refer to. Now we're going to work in the system, and so I would prefer it if you called them row 1, row 2, row 3, that kind of thing. And so you're going to write down what you're doing at each step. And if you're interchanging your rows, you use a double arrow, right? Just swapping those rows. So here, this is the first example. There's no room here So that's why you're gonna need the blank paper. And I'm gonna add a page here. Copy. Because pretty sure the school would be pretty mad at me if I printed all the space that we would need. Blank pages printed. Okay. So we're going to use the Gauss-Jordan elimination method to solve this system. Now this is our first one, okay? And as long as you remember that the goal is to have a coefficient of 1 on the x and a coefficient of 1 on the y in the second row and coefficients of 0 in the other two columns, like this, our goal is to have something like 1x, or maybe I'll just do x. X plus 0y is equal to something. And 0x plus y is equal to something. That's our goal. Okay. So this is where we need to get creative. And again, there's lots of different ways that you could go through and solve this. One of my my go-to moves, and it is not original because it's kind of core to matrix algebra, which is what we're heading towards and working with matrices, is if it's reasonable, I like to turn the coefficient of x into 1 just kind of right away, right? And so what I'm going to do is I'm going to write out this system. 2x minus 6y is equal to -8. And -5x plus 13y is equal to 1. Now at each step, I'm going to use an arrow that was kind of shaky there. And over the arrow, I'm going to say what move I made. Right? There's lots of different options, but I am going to take 1/2 times R1. Which means that row 2, you can just write it out as is. In fact, -5x plus 13y is equal to 1. Notice how I'm writing these kind of lofty so that it's really obvious that the x's and the y's and the results are stacked on top of each other. And that is because that's how matrices will work later. And it would be so messy. So now, in this move, I'm saying I'm going to take 1/2 times R1. So multiply all of R1 by 1/2. A lot of this is just kind of basic algebra. And so you can do it in your head. You don't have to show the actual work that you did. And so 2 divided by 2 makes 1x, or just x if you prefer. -6 divided by 2 minus 3y. Don't forget the other side. -8 divided by 2 is -4. Now, depending on how you like to stack your work, I'd like to see something like this, where your next move is just below it, or some version of that. And so now, what am I going to do? We could do that. How about I eliminate this little guy first, so I don't have to deal with -5 over 13. Ugh. So how can I eliminate this -5? I can take row 2 plus 5 times row 1. Right? Let's try that. So row 2 plus 5 times R1. Making note of the -5, so in order to set that equal to 0, because remember that's our goal here, then -5, I need to add 5, and I have 1 here. So row 1 is unharmed. X minus 3y is equal to -4. I just jot that down. And you do not wanna leave anything blank, even though it's tedious to write down the ones that don't change. You have to write them down because otherwise it'll make a real mess.
I thought you were multiplying 5 on row 1.
Ah, the manipulation is being done to row 2. So here, row 2 plus 5 times row 1 tells me that row 1 is unchanged by this, but row 2 is having 5 times row 1 added to it, which means -5 plus 5 times 1 makes 0x, which was my goal, right? Now, less breezy, I guess, is thinking about 13 plus 5 times -3. 13 plus 5 times -3. I have to cheat. I'm gonna go with -2. (13 minus 15) sold. -2y. 1 plus 5 times -4. 1 plus -20 makes -19. Then what's my next move? Now this, I don't even have to write anymore, really, right? I am gonna keep the 0x, but now I'm gonna turn my attention to this little guy, right? Because my goal was to have something just x plus 0 is equal to something and 0 plus y is equal to something. So I need to turn this coefficient into 1. How am I going to do that? I'm going to divide by -1/2. Sorry, multiply by -1/2. Because division is just multiplication. And I'm going to do it to R2. Row 1 stays the same. X minus 3y is equal to -4. 0 times -1/2 is still 0. So that's nice. And one of the main things that you want to keep track of is once you have a 0, you don't want to let it go, right? You don't want to do a manipulation that turns your 0 into a number again because you did a lot of work to get there. So then -2 times -1/2 is 1y. -19 times -1/2 is 19/2. I'm so close. My next target is this little guy, the -3y. I'm going to add 3 times row 2 to row 1. So here, row 1 plus 3 times row 2. 1 plus 3 times 0 luckily is still 1. And I'll just keep it 1x just to emphasize. -3 plus 3 times 1, or -3y plus 3 times 1y, plus 0y. That was my goal. That's why I was doing it. But I need to pay attention to the -4. So -4 plus 3 times 19 over 2. That's not, the easiest math, but your calculator will just do the fraction. So just make sure that your calculator settings are all good, and you're able to add that fraction easily to get 49 over 2. Then row 2 is unchanged. 0x plus 1y is 19 over 2. Oops. I have the solution. Therefore, x must be 49 over 2 or 24.5 if you prefer. And y must be 19 over 2 or 9.5 if you prefer. The heck? Doesn't want to do it anymore. Okay. How's that feel? Pretty good, pretty fun. I think. Gotta keep your wits about you.
Doesn't matter which one you state put. Well, you can just choose which row you want to change.
Yeah. Keeping in mind that the ultimate goal is to have something like this, x and y equal to something, right? Kind of this diagonal form.
And you can add or multiply or whatever you want, as long as the other side is remain and the other side change.
Yeah, as long as you're doing it to both sides, right? Which is usually what I tend to forget, is to manipulate the last bit of the equation, right? This side here. So you want to keep your wits about you. Do you want to know how to solve it on your calculator? Good for part marks on the test. No. Well, you heard it here first. Nope. Then I'm not going to tell you. I have decided, because these are our skills that we'll need, especially as we move into matrices. For full marks, you'll have to show me your matrix manipulations, but I want you to be able to check your work using your calculator. And so any sort of kind of engineering calculator will do it. And it's actually pretty easy. Let's see here. Do I have a picture of my calculator handy? Okay, just gonna crop this up. The new ones are fancier. They have like green on them and stuff. Oops. So you probably have, if you went to the bookstore, probably have a newer version of this one. Or let's see, hold up your, so I can see your faces. Okay. Yeah, so that's the newer version of this one. You probably have matrices on there, definitely. And so what you're gonna do is on mine, I go to menu setup and then I scroll down until I see, and then scroll down. Obviously, if it's a different brand, it'll be way different. You can Google it, but for me, there's an option that looks like this. XY is equal to 0. Here. So mine, I'll go to highlight it. How can I do this? My makeshift document camera. So here, I scroll down here, and then I go equals, and then I hit 1 for the simultaneous equations, I think it stands for. Polynomial degree. I have 3 unknowns. Hey, I think I hit something weird. Let me go back there. Yeah. 1. There. I did. I hit the polynomial menu. That's okay. Number of unknowns, that looks better. 3. And then what you can do is you can just fill in these equations. And then once it's all filled in, you hit equals and it'll just do it for you. That's kind of nice. Oh, I guess we had 2. Let me go back there. 1. See if I can do this kind of. We only had 2 unknowns for this example. That's nice. 2, -6, -8, -5, 13, and 1 equals. Gives me x is 49 over 2. And then I scroll down, y is 19 over 2. And then if I had more, I could scroll down through more. Wowee. Okay. That is kind of tricky. Try to summarize that here. Okay. Hit that button. And then hit the equals button. And then mine says 1, oops, simul equation or 2 polynomial. We want 1. Enter the number of unknowns. And then enter the system. And then hit enter. And then it'll give it to you. You don't have to use that. But like I said, what I've decided is if you're completely stumped, then you can just use your calculator for part marks, probably like 1 or 2 out of 5, right? Full marks, you have to be able to do the work. But at the end of the day, we're going to be working with word problems. And so that's going to be require kind of making the system. And so the math isn't, truly the hardest part anymore. So that's why. But I'll clarify that closer to the test. Did you find a matrix? Or, oh, sorry, not a matrix, some equation. Hey, you've even got your instructions. Study up. It's worth it for the shortcuts. Wouldn't it be so great if you didn't have to write the X's and Y's and Z's every time? Yes. And so that's where matrices come in. And so this here is our very first matrix. And isn't she beautiful? She looks like this. So we use square brackets and we only write the coefficients. Because notice when we were subtracting and adding the rows, we were adding and subtracting X's and Y's with each other, obviously, but as long as we've stacked them on top of each other, that kind of falls into place. And so we were ignoring the X's, which is what matrices do anyways. And so we can just write our coefficients like this. So 2, -6, -5, 13, and then -8 and 1. Now, this vertical line can be thought of as the equal sign from before. Yeah.
I just use now I put it's not irrelevant, but I'm just saying I put X on the other side and gave a value of X and put that in an equation on the other equation, and you will get the Y answer.
Yeah, so that's substitution.
And you can use that way to get the answer.
You can, but it's gonna be just a hot mess for more than 2. For 2, 3 unknowns, it's pretty reasonable still. But if you're using matrices, we're quickly gonna work with the elimination method instead. Right? And so, but I always prefer substitution because it makes more sense to me. And so I always start there. But then for matrices, when I move into matrices, then we start using the elimination method for matrices. Right? For this system, I don't care. In fact, I might say use substitution or elimination to solve this system. They're the same to me. All right, so whichever one you prefer is fine. Because our Gauss-Jordan elimination method will be tested in the matrices anyways. So you will have to use it for the matrices. And so what does this thing look like? Each row of the matrix corresponds to an equation, and each column of the matrix, so this guy and this guy, X and Y from before, corresponds to a variable. So the diagonal form of a matrix, which remember was our goal from earlier, was to have 1, 1 on the diagonal and zeros around it, right? And then the result is solution 1, solution 2. So that's nice. And so I'll just highlight that you want to have 1s on the diagonal, zeros everywhere else. Okay. This is from that previous example, but luckily, maybe I'll add a page up here instead. Use a matrix with elementary row operations to solve the system. So the row operations stay the same. You're allowed to move rows around, right? You're allowed to rearrange these rows as long as you keep them together, okay? That might be in situations where if you have an obvious leading 1, for example, or coefficient of X, then I would usually float that to the top and just use that instead, but it's up to you. You're allowed to multiply by any number as long as you do it to the entire row, and you can add or subtract multiples of other rows to the, or of a row to other rows. First task is to write this thing out as a matrix. And so making sure, I did a poor job of stacking these because I was being lazy, I guess. But making sure you kind of write it nice and lofty. A matrix has square brackets and only the coefficients, or we only need to write the coefficients. 3, -6, 9, 0. Maybe I'll give myself slightly bigger brackets because I have 3 equations and 3 unknowns now. So that vertical bar just separates the solution, just so you don't accidentally turn it into a 1 and try to pivot around it. Right. 4, -6, 8, -4. You want to be really careful with your positives and negatives because they'll make a huge difference. -2, -1, 1, and 7. Now, I'll give you a heads up. I did 1, 2, 3, 4, 5, 6, 7 row operations, but 2 of them I doubled up. So technically there's going to be 9. So I do start to kind of chain link them because otherwise you're going to go through just a ton of paper. And so I'll start writing it like this. And if you see kind of quicker moves, that's great. But like I said, I just kind of encourage you to think about what comes to you naturally and then just kind of embrace that and nurture that. So for me, if I don't see an obvious choice for the first row, right, then I'm going to take this first term and I'm going to divide it by 3. And luckily, in this case, dividing by 3 works, right? If I got a nasty fraction that I had to deal with throughout, I would maybe reconsider and maybe use something else as my row 1 to interchange them. But in this case, 1/3 times R1 works for me.
Minus the second row.
Yeah, so there's, so the more you work with these, you'll start to see, oh, I see a fraction coming down the road. I don't want to deal with that. How can I avoid it? Right? Are there things that I can do? Right? Like I can use this little guy to eliminate this 4, for example. Right? It doesn't have to be this one. But when we're first starting out, it's nice to have kind of a nice starting point, right? And so dividing each term by 3 in row 1, I get 1, -2, 3, 0 divided by 3 is 0 still. The other 2 are unchanged, so just don't lose any negatives or positives, and you'll be good to go. On your calculator, you would tell it that you have 3 unknowns, and then it would adjust it and give you 3 equations to fill in. So you can easily check your work, but like I said, there's a lot of work that you have to do for full marks. So here's where I start getting a little bit cheap with my virtual space, I guess. And I'm gonna apply my next move down here. Usually I would stack them. So my next move for me is, what if I take away 4 times row 1 from row 2? Sure, start chipping away at these guys, turning them into zeros, right? Because that's my goal. And so from row 2, I'm gonna subtract 4 times row 1. row 1 stays the same, 1, -2, 3, 0. Row 2 is changed, so 4 minus 4 times 1 is 0. -6 minus 4 times -2. Uh-oh, what do I have? I think I've got 2 here. Let's confirm. -6 plus 8. Oh, phew, 2. 8 minus 4 times 3, I've got -4. And -4 minus 4 times 0, -4. You are allowed, instead of just writing out this unchanged row, because it doesn't hinge on what happened in row 2, you can also manipulate row 3. If that's what you're doing in one move, you're allowed to do something like this, row 3 plus 2 times row 1. Just to save you a little bit of kind of writing. And so then I have -2 plus 2 times 1, 0. Being careful that you don't kind of switcheroo these equations. Right now we're working with R3 plus 2 times R1. And if you want to break it up and do just one move per matrix, that is a-okay. And so I have -1 plus 2 times -2, putting me at -5. 1 plus 2 times 3 puts me at 7. And 7 plus 2 times 0 is 7. The math is not bad, but you do have to stay flexy.
If you're doing that twice in one column,
Yep.
do you use row 2, or do you have to only use row 1?
I don't want you to use row 2 because it was just manipulated here. And so that would be kind of using the previous row 2.
Oh, that's not meant.
But you've already.
Previous.
Yes. But I wouldn't, because then you manipulated row 2 here already. So I think it would get too messy. And remember, the move is to keep this 1 and then just leverage this 1 to make these 2 zeros. So you don't actually want to touch on row 2 yet. Right? And so now we have these guys here. So now what I'm going to do is I'm going to do the same thing with this next row. I'm going to turn this 2 into a 1. And then I'm going to use this 1 to turn this into 0 and this into 0. And then I'm going to chip away at the columns. And then my last move will be turning the 7 into 1 and turning these 2 above into zeros. But I recognize that I'm out of time, but what a great question to leave you with to try on your own. And then we'll, I guess I'll finish it in the video. Hey, that's clickbait. You won't believe what happens next. I'll finish it in the video for Friday, and we'll keep going through these for the video. Have a great long weekend. I know it's a ways away, but enjoy it. And I guess I'll see you the following Friday. Weird, crazy. If you have any questions, let me know.